Terms and definitions. The purpose of this video is simply to talk about the terms that exist in Maxwell's equations, talk about what they mean. Yes, we'll get a bit into Maxwell's equations and some electromagnetic theory, but really I mean to teach those concepts later. Here we're just focusing on the terms themselves. Maxwell's equations. Let's start by presenting Maxwell's equations. And we won't talk about the equations themselves until a later video here. I'm just presenting them so we can look at all of the terms that exist inside of them. We'll start with the time domain integral form of Maxwell's equations. In my opinion, this is the most general form. When we jump to one of the other forms, I think we lose information. We can Fourier transform these equations and jump to the frequency domain form. When we do this, however, we lose the transient time domain sort of information that we had in the time domain form. We can also write these in differential form. Immediately, we can see that these are simpler equations. And we'll end with Maxwell's equations in the frequency domain differential form. And in my opinion, these are by far, I think, the most common way that Maxwell's equations are presented, and they're the easiest to work with. Now, if we stare at these equations long enough, what we'll see is that these equations really only contain field terms. What about the materials? How do electromagnetic waves interact with materials? Well, the material properties are not inside Maxwell's equations. So in fact, Maxwell's equations do not directly tell us how electromagnetic fields interact with materials. That information comes from other equations. These other equations are often called the constitutive relations. And here we have our material properties. We have the permittivity, which is talking about the electric response of materials. And we have the permeability, which is talking about the magnetic response of materials. So in conjunction with Maxwell's equations, now we have a somewhat complete picture of electromagnetics. The only thing we're still missing that would describe all of classical electromagnetics is the Lorentz force law, which describes the force that electric and magnetic fields would put onto a charge. Let's just run through some quick notes about Maxwell's equations. The time domain integral form is the most general. All the information that comes from Maxwell's equations fundamentally comes from these equations. All other forms, we lose information. The frequency domain differential form is the most common, and I think that's because they're the simplest form and the easiest to work with. It's interesting to note that while everything comes from Maxwell's equations, the equations themselves are rarely useful. Instead, we start with these equations and we derive a whole bunch of stuff, and after a series of steps, we get to equations that we actually use to design devices and calculate fields. But it's rare that I just plug numbers into Maxwell's equations and calculate something. In fact, I'm not sure I've ever done that. Maxwell's equations do not directly describe how fields interact with matter. We saw that that came from these constitutive relations. And that's because the material property terms, permittivity and permeability, don't exist in Maxwell's equations. Another thing we could notice if we looked at Maxwell's equations is that the electric fields do not directly experience permeability. The electric fields will only experience permeability indirectly through their coupling to the magnetic fields. Likewise, magnetic fields don't directly experience permittivity. The magnetic fields only indirectly feel that through the coupling to the electric fields. Terms and definitions. We'll start with the electric field quantities. And here's how I like to describe it. There's two ways that we can have electric energy. First, there has to be energy in the field itself. And we know this because electric fields can transport energy through the vacuum of space. And in the vacuum of space, there is nothing. They didn't know this in the old days. They used to call it the ether because they could not imagine a wave somehow propagating through nothing, but electromagnetic fields do that. So we know that there's energy in the field itself. Let's call this the electric field intensity E. We can also have electric energy stored in matter, and this is in the form of displaced charge. And the picture I'm showing here, we have atoms. The little red dots are the nucleuses, and the gray region around that is the electron orbital. And if we could stretch those electron orbitals, that's very much like a mass on a spring. That orbital wants to spring back to its equilibrium position, and we can stretch those by applying an electric field. Well, each one of those atoms that has this stretched orbital is storing a little bit of electric energy. And when this is happening, we call this material polarized, and we're writing that with this polarization vector P. So we have two ways to store electric energy, in the field itself and in the form of displaced charge. So the electric field intensity, this is the form of energy that exists in the vacuum of space. We'll give it units of volts per meter. So clearly this is most closely associated with voltage from circuit theory. It'll also turn out it's most closely associated with force. It's the initial force that we would put on a dielectric medium that would displace these electron orbitals. So when we apply the electric field, it stretches those electron orbitals, and it comes from the Lorentz force law. For electric fields, the force on a charge is simply the charge times the electric field. The electron orbitals have a negative charge. The nuclei have a positive charge, so they get forced in opposite directions and they get stretched, and that's storing the charge. But the electric field intensity is just the push that does this. When a material has these electron orbitals stretched, we call it polarized. And the vector we describe this with is the electric polarization. This is the second way that we can have electric energy. We'll give this units of coulombs per square meter. Coulombs is the unit of charge. Now we apply an electric field intensity E, and it becomes polarized with vector P. So we have a couple of constants here that help us convert the units of electric field intensity to polarization. First, we have what's called the free space permittivity. And this is what carries all of the units. That's farads per meter. That will convert volts per meter into coulombs per meter squared. We also have this chi term. This is called the electric susceptibility. It does not have any units, and it is a measure of how easy it is to polarize. So if we apply an electric field that has a strong or high susceptibility, those electron orbitals will be easily stretched, so it stores energy more easily. Think of that really as just the constant of proportionality between E and P, and this epsilon naught is converting the units between E and P. Then we arrive at the electric flux density, D. This is the all-inclusive electric field term that accounts for both ways to have electric energy. It includes the energy in the field itself, plus the energy that we store in matter. And we can, I guess, choose to give it units of one or the other. We're going to give this units of coulombs per square meter, same exact units as the polarization. And since we understand that polarization is really sort of displaced electron orbital, sometimes this D is called the displacement field for that term because it's quantifying the displacement at the atomic scale. However, it's not just that, it also includes the outer space sort of version of electric energy. So that's our electric flux density, units of coulombs per meter squared. It is most closely associated with charge. So when we're calculating fields around charge, we will do that for the electric flux density. We will repeat everything we said for electric fields, but for magnetic fields. And it turns out there's two ways to have magnetic energy. First, there's energy in the field itself, and we know that because magnetic fields can transport energy through the vacuum of space. We can also have magnetic energy stored at the atomic scale, and this is called magnetization. In some molecules and atoms, the electron orbitals are more donut-shaped, and the electrons spin in this sort of circular pattern. And anytime we have charge moving in a ring-type pattern, that induces a magnetic field through the center of that circulation or through the axis of that circulation. Now, in an ordinary material, these magnetic dipoles, if you will, they're randomly oriented. But if we apply a magnetic field H to them, they will tend to want to align along the same direction as H. They want to spring back to their equilibrium position. So again, it's like a mass on a spring. It's storing magnetic energy when we align these, but they want to spring back. And if we release that magnetic field, they all spring back to their equilibrium position. So we can store magnetic energy in matter also. And we will describe that through this vector M, magnetization. The magnetic field intensity. This is the form of magnetic energy that exists in the field itself. We will give this units of amperes per meter. And of course, amperes is the unit of electrical current. The magnetic field intensity is most fundamentally related to electrical current. So anytime we're calculating magnetic fields around different types of current, we will do this through the magnetic field intensity. It's also the initial push on these atomic scale magnetic dipoles that will tend to align them. So what I'm showing at the bottom here is some material that has these randomly oriented magnetic dipoles before there's any magnetic field applied. If we go ahead and apply a magnetic field, those magnetic dipoles will tend to align with the magnetic field. But they're like masses on a spring. They want to spring back to their original equilibrium position. Thus, they're storing energy, and we're storing magnetic energy. But the magnetic field intensity is simply the push that would align those dipoles. Now, the form of magnetic energy stored at the atomic scale, this is called the magnetic polarization. And we'll call this a vector M, and it has units of Webers per square meter. If there was such a thing as magnetic charge, that would have units of Webers. But a lot of times, rather than call this Webers per meter squared, we'll give this unit Tesla, or we'll just call it Tesla. Now, in order to convert the units from magnetic field intensity, which is amperes per meter, to magnetic polarization, which is Tesla or Webers per meter squared, we convert the units through the free space permeability. And this has units of henries per meter. We also have this chi term, chi sub m. That is the magnetic susceptibility. That's a measure of how easy it is to align these magnetic dipoles when we apply a magnetic field to it. So the larger this magnetic susceptibility, the more easily these dipoles will be aligned, and we'd expect more interaction between the material and the magnetic field. We move on to the magnetic flux density, or the B field. This also has units of Tesla or Webers per meter squared. So it's the same units as the magnetization. This is the all-inclusive term that includes both forms of magnetic energy. It includes the energy in the field itself, plus the energy stored in matter. And so it has the same units as the magnetization. So we need to convert the units of magnetic field intensity. So we're including the free space permeability here. Now, the magnetic flux density is what's most closely related to force here. So the needle on a compass, for example, would tend to align with the B field. I want to briefly mention magnetic polarization versus magnetization. These are essentially the same thing. They're different by one constant, but it can lead to some confusion if you're following along with another textbook. So in this book, we are writing our constitutive relation as B equals mu naught times H plus this vector M, which is the magnetic polarization. And we're writing it this way to show parallels to the electric field constitutive relation. In a lot of textbooks, this is written in terms of what's called the magnetization. And unfortunately, often this is the same capital M vector, and it's very confusing, but we need to multiply by a mu naught here. So the magnetic polarization has the same units as magnetic flux density. So that's Webers per square meter or Tesla. And magnetization has the same units as magnetic field intensity, which is amperes per meter. The two terms mean essentially the same thing, and they're related through this constant mu naught. So hopefully this clears up confusion. We move on to the electric current density. This is a J written as a vector form, and it's a density, so it's something per volume or area. And in this case, it's amperes per square meter. So it's the electrical current distributed over some area. So down below, I'm showing a conductor, and the flow of charges is throughout the volume of this conductor. But if we just look at a cross section and we think of it as maybe a whole bunch of little tiny currents at each little point, this is the current density. And so if we add it all up through an integration, if we integrate over the cross section of that conductor, so we're integrating our electric current density, we would get the total current. And this total current is what we use in circuit theory. There is also the volume charge density. Think of charge as sort of like a cloud, how I'm showing here, and that charge can change as a function of position. It's a density term, so it has units of coulombs per volume, cubic meter. Coulombs is the actual unit of charge, and when we divide by volume, this is the volume charge density. So if we have some charge cloud, if you will, if we wanted to calculate the overall charge, we would integrate that. And so we need to do a volume integral here. So the volume integral gives us our overall charge. Now, if it was a constant charge density throughout the volume, that's not what I'm showing over here to the right, but if it were, then the total charge would simply be the charge density times the volume. Anytime we have a label of any kind of density, there's always an integral equation hiding behind it to add it all up and get a total quantity. And so here our volume charge density has this volume integral hiding behind it to get the overall charge. Permittivity. Permittivity is a measure of how well a medium stores electric energy. Notice I called it a medium and not a material. And this is because the vacuum of space also has the ability to store electric energy, and that's in the field itself. So I'm calling it a medium. And in fact, the permittivity accounts for both the ability of a vacuum and matter to store electric energy all at the same time. We can loosely more think of it as just how much as a measure of how much the electric fields interact with a material. But fundamentally, it's how well a medium stores electric energy. From circuit theory, we know that capacitors store electric energy. So permittivity is most closely related to capacitance. So we have our overall permittivity. We tend to write this as a product of two terms. We have our free space permittivity, which is usually in calculations 8.854 times 10 to the minus 12 farads per meter. Now that's a crazy number. We don't like to talk and communicate to each other using these crazy type of numbers. So what we do then is we multiply the free space permittivity times a relative permittivity, also called the dielectric constant. And so this is the ratio or the factor by which the actual permittivity differs from the free space permittivity. This is a much more convenient number. So the vacuum of space or even air just has a relative permittivity of 1. That's an easy number to communicate. Plastics tend to have a relative permittivity around 2.5. Ceramics, 6 to 10, maybe even 20. And there's exotic materials that have relative permittivities or dielectric constants even much higher than that. But it has no units, and this relative permittivity just tends to be a much more convenient unit. But make no mistake, the relative permittivity is not the permittivity. We need to multiply by the free space permittivity to get the actual electric permittivity. We can say everything we just said about permittivity for permeability. Permeability is the ability for a medium to store magnetic energy. And this includes both the ability for vacuum of space to store magnetic energy in the field itself and the ability for matter to store magnetic energy in the form of these rotated or tilted magnetic dipoles. We can a bit more loosely think of this as just a measure of how much the magnetic fields interact with the materials, but truly it's a measure of how well it stores magnetic energy. Well, from circuit theory, we know that inductors store magnetic energy. So permeability is most closely related to inductance. Like the permittivity, we can write the permeability as the product of two things, the free space permeability and the relative permeability. Now, the relative permittivity we call dielectric constant. There is no other sort of loose term for relative permeability, so we'll just keep calling it relative permeability. But it's a much more convenient number to use, right? The free space permeability is this crazy number, 1.2566 times 10 to the minus 6 henries per meter. Well, that's an ugly number to communicate in a conversation, so we tend to just communicate this relative permeability, which is a number like 1 or 2 or something like that. Much more convenient and also has no units. Conductivity. This is written as the Greek letter sigma, the lowercase, and it has units of 1 divided by ohm meters. Conductivity is a measure of how well some material conducts electricity. Now that can be a flow of positive or negative charges. We tend to think of this as just negative charges or electrons in a metal like copper or aluminum or something like that. There's also resistivity, written as a lowercase Greek letter rho. This has units of ohm meters, and it's simply 1 over the conductivity. So conductivity and resistivity are essentially interchangeable terms. They're just reciprocals of each other. Resistivity would then be the ability of a medium to resist the conduction of electricity. We have an Ohm's law in electromagnetics. From circuit theory, this was a V equals IR type of equation. Now for electromagnetics, we have a J, the electric current density, equals sigma times the electric field. So if we apply an electric field to a conductive medium where there's free charges, that will conduct an electricity. And there will be some current density flowing through that medium. The total current then, if there's a constant current density throughout the cross-section, would simply be the current density times the area. If not, then we have to integrate. If there's not a constant current density throughout the volume, then we'd have to integrate to get total current. Types of electric current. It turns out there's 3 major types of electrical current. Let's talk about these. The first, and probably the one you're most familiar with, is called the conduction current. And so we'll write this with a lowercase sigma to remind us that if a material is conductive, this is the type of electrical current that will allow. So it's the flow of free charges through conductors. This is the kind of current that you studied in circuit theory and why I think this is the most familiar one to you, but it is not the only type of electrical current. The second one is called the convection current, and I have a subscript epsilon. This is the permittivity, really just to remind us that this is a flow of charges through insulators. That's very interesting because we think of insulators as not allowing an electrical current, but in fact, that can be the case. For example, have you ever on a dry day blown up a balloon, rubbed it on your hair, and stuck it to a wall? You have transferred charges there, but there's no conductors. That's charges flowing through insulators. And in fact, those types of currents obey different laws that we'll get into. The last type of current is the displacement current. And the subscript D is to remind us this is sort of related to the displacement field that we talked about. Remember when we talked about the two types of electric energy, and we showed the atoms and they're in their equilibrium state. We apply an electric field and that stretches those electron orbitals to one side, forming an electric dipole. Well, during that time where those orbitals are stretching from their equilibrium state to however they're stretched, there is this momentary movement of charges, and that is a current. And so we have to count it as that, and it is called the displacement current. It's a very short-lived current. So at this point, we can talk about the total electric current. And so the subscript T is remind us this is the total, and it's the sum of all three. All three is the movement of charges, so all three are electrical current. Conduction current. We can apply an electric field somehow, and this is the flow of charges through a conductor. Most often, this is electrons moving through a material like a copper wire. And in this case, it's obeying the Ohm's law for electromagnetics, where the current density, and we're putting the sigma here to remind us it's just the current density for the conduction current, equals sigma times E. This current obeys that law. Convection current. This is the flow of charges through insulators. Of course, there has to be charges in those insulators for this to happen, and we apply an electric field, and that would move those charges. Now, interestingly, this type of a current does not obey Ohm's law because there's no conductors involved. So we can define our convection current this way. We have some charge density in that insulator, and they're moving at some velocity v. So the product of these two terms gives us the current density for the convection current. Now I mentioned this current doesn't obey Ohm's law. What law does it behave or follow? It's called the continuity of current equation. On the left, we have del dot J. This is a measure of divergence. We're calculating how much the current tends to diverge or converge to a single point. Well, if there is current that's converging to a point or diverging from it, clearly we're either accumulating or losing charge at that point. And that's exactly what the right-hand side of the equation is explaining. This charge density must be changing with time if there is current diverging from it or converging to it. And the last, we have our displacement current. This is when we apply an electric field, we have our electron orbitals in an equilibrium state. When we apply the field, they become stretched. Well, there's this momentary displacement of charge here. That is a very momentary current. And so when the electric flux density is changing, the only way that that can be changing is if there's a displacement current happening. Let's end our discussion of current with talking about the total current. And we mentioned the total current density is conduction current plus convection current plus the displacement current. The first two, the conduction and the convection currents, these are currents due to free charges. Now those charges could be in a conductor or in an insulator, but it's free charges that are moving. We tend to lump these together and just call this J. And this is the J term that we see in Maxwell's equations. The J term in Maxwell's equations does not include this displacement term. That's accounted for in the derivative of the electric flux density. So even though this is a current, it's just treated differently in Maxwell's equations. Duality. To get into the duality of Maxwell's equations, let's write these equations in a form that shows off the symmetry. So I'm going to make up two non-physical things. I'm going to pretend that there's such a thing as magnetic charge, which means there is a magnetic charge density to sort of go along with and be a dual with electric charge density. Then there would also be a magnetic current density to sort of mirror and be the dual of the electric current density. When we write Maxwell's equations this way, the duality becomes much more apparent. It's like whatever we're writing for electric fields, there's the exact same equation for the magnetic fields. And that's the origin of the duality. So the electric field quantity E has units of volts per meter. This is the electric field intensity. Well, the dual term for the magnetic field, that's the magnetic field intensity with units of amps per meter. Both of these are the form of electromagnetic energy that exists in the field itself. And these are what's most closely related to electricity, voltage, and current. We then move down to the electric flux density and the magnetic flux density. Both of those are the all-inclusive terms that contain both forms of electric and magnetic energy. We could then move to the current, where we have the electric current density and the magnetic current density. We can talk about the electric charge density and the magnetic charge density. And then we can talk about the permittivity, which is the ability of a medium to store electric energy. And we have the permeability, which is the ability of a medium to store magnetic energy. Now, the non-physical terms are what I've highlighted in red here, but it does help show off the duality. Now, why is this even important? Let's end with some notes on duality. I love this part. It's a self-check for derivation. Since they're roughly equivalent, I should be able, if I do a long derivation and end up with an expression for an electric field, I should be able to go back and do an equivalent derivation and end up with the same expression, but for magnetic fields, where E is swapped for H, D is swapped for B, the permittivity is swapped for permeability, and the electric charge density and electric current density are swapped for the magnetic charge density and magnetic current density. And so I can do the derivation twice, and if I get the same answer, that's a pretty good check that I've done the derivation correctly. And I do this all the time. The other one is actually a physical thing, some design freedom. If we're reading the literature and we see this really cool magnetic device, but you know what? We don't have materials that have that kind of permeability. Well, if we could find materials that have that same permittivity, we could build a device from permittivity instead of permeability, and it turns out that it would behave the exact same way, just with the roles of the electric and magnetic fields reversed.